Hello, everybody. Good afternoon. My name is Elisa Sayrol. I'm also a member of the group of image and video processing. And like all of us now, I'm working on deep learning. And one of the topics that I'm dealing with is medical imaging. And today I'm going to give an overview of this topic and then some examples of works done by some of the professors and students of the group. So just let me see that in, oops. Is it working now? So, do you know if there is a command to a click? Yeah, was it there yesterday or no? It was here this morning. No? Sí. So I'll stay here. Okay, so just to tell that myself with Veronica, we work together, and she's also working a lot in, actually she works exclusively on medical imaging, and some other members of the team also work on medical imaging. And first I will explain why deep learning for medical imaging, then some of the challenges that we have to face if we are working in images, in medical images, and then some of these applications that I told you. So let's see that if you want to know a little bit more about this I forgot about this topic, you may go to this survey. It's not a recent one, but it's very well explained. What are the different problems that you have to face, the different applications. And also in this survey, you're going to see that how the use of medical imaging and medical informatics, here it's only 2015, but you will see that it grows a lot, and especially medical imaging. And also if you go to medical imaging per se, you will see that also it's growing a lot, and the use of CNNs, of convolutional neural networks, is the one that has more impact in research on medical imaging. So it's a hot topic of application of deep learning, and one of the most popular applications is magnetic resonance imaging, especially images of 3D from the brain. But you also have a lot of applications in images taken by the microscope, from the blood, from different tissues. So from observing images from the microscope, you can take also a lot of information. Also computer tomography. Instead of magnetic resonance, it's taken with X-rays, and actually you have 2D X-rays and ultrasounds. And with low energy X-rays, you have mammographies. You may have other kinds of modalities to obtain the images, and finally the last one, which was very popular because one of the first topics to be successful with deep learning was in color fundus photos, which are photographs taken from the back of the eye. And well, so these are the main applications. Modalities of the images, but from here, which are the areas? So the most common one are to take pathologies. Pathologies, that the classical example would be images from microscopy, observing the tissues or blob, or obtaining bacteria or viruses, or from the blood, or observing the cells. But also the second application is from MRI images of the brain to detect tumor, to analyze possible impacts of Alzheimer in the brain. You can also, other applications are images from the lungs, from the abdomen through the, to observe the different parts of the abdomen, the heart, the breast. In the abdomen you will have the organs, the liver, the stomach, etc. And also breast, also images from the bones, to see fractures and so on. And as I was mentioned, also from the eye to observe the possible problems in the retina. The kind of algorithms that you may apply to these 2D or 3D images range from segmentation. If you want, for example, to extract the position and to recognize where you have an organ in one of these images, or within an organ to segment where you have a lesion within this organ. You may also want to not to segment, but to detect some parts, for example, a lesion in this case, but not necessarily to have the segmentation. You may have problems of classification. For example, say this image has skin cancer or not, just to say yes or not. So that exam classification will be a binary decision. If it's not binary, then we may classify types of cancers or types of different pathologies which you only need to classify. Okay, and other tasks would be, for example, to do registration from MRI images. You have different projections. So you may want, which give different information. You may want to see the correspondence of the voxels of the pixels if you take different images. So it's also an important problem. You may also want to enhance images or to combine information from your images to some other type of information, like say, what if the image that you are seeing belongs to a male or a female, or it's from a young person, an old person, or the exposures to some illness depending on where you live, etc., etc. So you may combine images with other information to extract or to take decisions. So this area of application of deep learning or in computer vision in general, it's challenging in the following sense. One is that regarding the way we work, engineers, versus the way medical doctors work, and see the importance of what it's the information per se. So one thing that could be important for us is not important for the medical doctor, or vice versa. So we need to gather and have a lot of discussions and conversation to know even what is the goal, because you say, oh, yes, I understood, but maybe you didn't understood what the medical doctor was saying. Also, another challenging problem is that the physiology of a human person, which, for example, the shape of the liver or the shape of the brain or the way a person can develop a tumor is very different from one person to the other. So these differences of physiology make difficult to even to annotate images, to make predictions. And as regarding this topic, it's also difficult to, okay, the medical doctor gives you instructions, but it's difficult to get from these instructions of the medical doctor to afterwards we have to program something. So how can you pass this valuable information to something that can afterwards work? Also, sometimes you talk to two different doctors and they have contradictory opinions, so that's a very challenging problem, especially if you are in front of two doctors that say opposite things, so that's terrible. Another thing is that sometimes the deep learning is like a black box. You don't know what's happening there, and that makes that some doctors say, okay, I cannot understand what this box is doing. Even sometimes for some legal purposes, you have to describe and give an analytical description of your algorithm, and if it's a black box, it's complicated. And this creates some lack of confidence on the algorithm. So this is a challenging regarding this problem definition and expertise, but also it's also challenging regarding the data, because many times you have data sets, but these data sets are not annotated. And if you want experts to annotate it, they say, okay, they give you the data, they maybe annotate a couple of images, and then you spend 1 month going after the medical doctor saying, please, can you annotate this? And sometimes it's challenging to get annotated images from experts. And also, you see that sensors are different. Different sensors can give you with this, to the same image, different results. And sometimes there is a class imbalance, especially when you are segmenting tissues or images where maybe the lesion or what it's of interest is very small and you have a huge background, and what you need to know it's very small. So this creates a class imbalance, especially when doing segmentation, or sometimes when it's a binary decision, you also have a lot of negatives and very few positives. So it's a problem that you also have to face with. So let's go now to some examples, and the first one is from brain tumor segmentation from MRI images, where you may have you have the 3D data, and usually to visualize, you take some slices, which can be axial, coronal, or sagittal, and from those images, you usually may mark where you have the lesion. Let's see more exactly an example. So in MRI, as I say, you have from the same sensor, you get different types of images, which is why it's called multimodal MRI images. Depending on the information, T1, T2, flare, you see that the image that is formed is a little bit different, but so you have to register them, and you can use the information in all of them to localize the tumor. So here you have this example where you have like the large area where is the tumor, which is called the edema, and then the non-enhancing solid core, which is the red area, And then here you have the core, which is the blue one, and in the middle, the green one, which is the necrotic part of the tumor. So this would be an example of one problem where you have to do the segmentation and detect these 4 areas, for example. So with Veronica, she has been working a lot in this topic, and also in Alzheimer images, and like we participated in one challenge to detect this tumor, and we applied different architectures. So you will see, in general, the architectures are well known for you, but the thing here is to apply it to this kind of problems. Okay, so you will see a network which is instead of 2D, it's a 3D extension of a fully convolutional network. Very popular second choice was to use a UNet or a VNet, which is a kind of network for segmentation in medical imaging that it's used a lot. I don't know if someone else maybe has told you, okay. And then there was some network which was in 2D and not very complicated, but that gave good results, okay. So I will go fast to these networks because, as I was telling you, I want to stress the application, not the architectures per se. And so here you see this 3D network where skip connections were used. As you can see in this network, that this is the depth network, and you take skip connections in a couple of places, and then you use all this information to generate the 3D map. This is the classical UNet. So also with these, the upsampling and downsampling and upsampling branches, and with skip connections that give, as you know, the details of high resolution in the upper layers and the low resolution with more information of global information in the down layers. Okay, so this was the second option, and the third one was something which used a combination of classical architecture with upsampling and an upper block, which did a large, I mean, a unique step on this part, and you unite both branches and get also a prediction of the 3D segmentation. And here are some of the results in different projections, just to see that the measures that were used were accuracy, die score, precision, recall. Okay, and the die score is kind of an intersection over union. Here you have a plus. This measure is quite used in medical imaging in segmentation, and you could see the comparisons of the three networks with the different projections, and you can compare with the ground truth. Okay, and this network worked better than the other two. Well, you can go to the paper if you want to have more details on the values that you have here. And well, let's change completely off topic. This was a problem you have an image of the skin, and you have some areas of the skin that can have sun, they are burned by the sun-exposed skin. But not all, I mean, you have a data set with images of sun exposure and some of them did not have this sun exposure, so it was a binary decision. And the problem here was that these images are high resolution, they are huge, and you have to divide the image in patches. So it's very also common in a medical image to divide the very high resolution images in patches. And here they were studying the way to take these patches and how is the selection of patches to decide which images were sun exposed images of the skin, using also an algorithm which is based on multiple instant learning to decide if these images were sun exposed. So, so the main idea is this: how you select these patches, and like they were compared just to do a regular grid sampling, taking the centroid of the patches, using a uniform distribution, or doing a Monte Carlo sampling. And the results of classification of this binary classification were better. I mean, we're betting for training, for the training accuracy, but of course that counts. What counts is when you use validation or test accuracy, and this way of sampling patches was a better one. Let's go to another problem as the ones that we have seen in this classification. So we have seen 3D segmentation, a binary decision classification. So this one is like an enhancement of images, where you have to, from low resolution images to obtain high or higher or super resolution images. Okay. So for this purpose, you use a GAN network, and it works in the following way. So for the discriminator part of the GAN, your input is either a super resolution image or a true high resolution image, and the discriminator has to decide if this is super resolution or high resolution. Okay. And the loss function for the discrimination is the least squares. And for the GAN, for the generator, you use a set of convolutional layers where you have several skip connections around. I mean, you use residual blocks. And then you have 3 different ways to do the upsample to get at the end the super resolution image. Okay, so either you use like a nearest neighbor upsampling, and then you use convolutions, or directly it's like you were using subpixel upsampling. It's like having using directly some filters at subpixel precision, but through I mean the convolutional layers. And these 3 possible ways to do the discrimination were compared to just doing like an interpolation, a cubic interpolation, and here a couple of 2 different upsamplings were tested, like upsampling by 2 or upsampling by 4, and you can see. I mean, here's, as I say, it's the interpolation, and here the 3 proposed solutions to get this super resolution image. And you could see that, I mean, regarding PSNR, the subpixel using the 3rd solution was the one that, with near neighbors, was the one that gave better results. But if you go to this other measure for similarity, the resize upsampling with nearest neighbors and then convolution was giving a better value of this similarity measure. Okay, so this is another application for medical imaging. Let's see another segmentation example. Okay, I'll take 5 more minutes. So here, the goal was to do the segmentation of a lesion in a liver from computer tomography images. So the proposal that Mirja gave was to do first liver segmentation. That is first to localize where in this computer tomography you have the liver. And as you can see, I don't know if I have it in the pro, but you have like a convolutional, different layers of convolutional neural networks. And also you, at the end, you take different resolutions, you upsample, and you add. Okay, so you also take skip connections to form the segmentation of the liver. And this information, together with some information which was using bounding boxes to detect or to localize where you have these lesions, are located. Okay, so I think if it was more than 50% of pixels have a lesion, these are positive. If they are not, they don't have any pixel, less than 50% of pixels are of the liver lesion, so they are negative. Okay, so you also train it here a deep neural network together to the liver segmentation, to at the end using this information to obtain the segmentation of the lesion. Okay, so this was the topic that well, here is the detection of the lesion tissues, and here were some results. They were not incredible, but they improved a little bit previous the baseline. Okay, the segmentation of the liver is used by the third network to do backpropagation only on those areas where you have liver. So it's a way it's a way to cope with the class imbalance that I mentioned at the beginning. Okay, so this was only using segmentation. This is using the detector of bad tissue or good tissue, and this was using a post-processing of conditional random fields. Well, this is also an example of, this is a microscope image where you have some parasites, which are the parasite of Leishmaniasis, and you have to detect if the images have this parasite, and if the parasites are inside the cell or outside the cell. Okay, and well, it was using a UNet. I will go fast, and the results. Well, this was the annotation tool, and some of the results are here. Okay, so it's using the UNet. We use also the UNet to detect the bacilli of the tuberculosis in sputum samples. And we are working still with this problem right now. And just I have a couple more of examples. This one was, it's interesting because it's a way, as I said, we don't have, one of the challenges of medical images is that we don't have so many annotated images. So to cope with this problem, one of the things that may be done is, okay, we use a first iteration of one algorithm that gives classifications, and the ones that have high certainty of being from one class or from another class, this can be automatically labeled. And those which are near the, in a binary problem, that you are close to being from one class to the other, those have uncertain probabilities, so this can be labeled by humans. This, in this paper, they also talk about uncertainty maps. So these maps can be, there are many ways to generate uncertainty maps, and one of them is to generate inferences, different outputs of inferences, but using dropout. So every time your image goes through the network, since the dropout has a maybe high probability to use some neurons or others, the result is different, okay? And I mean, it might be different. The thing is that it is different in those regions where the algorithm has some uncertainty. So usually when you have to segment some images, usually you are very certain the result is always the same, maybe in the inside, it's always the same in the background, but you have areas where, depending on the inference of your dropout, the algorithm doesn't know if it's belong to the background or to the object that you are trying to segment. Okay, and this information can be used also for this active learning. And well, you have, if you look at the paper, some comparisons between this active learning model and the true level, and see how you can get better and better results. And the last example, it's a very simple one. It's only using a VGG, but the thing is that usually when you train and you label, you might think that you are going to use the perfect segmentation of your object. But sometimes it's better not only use the perfect segmentation, but the area which is around the object you want to detect, okay? And in this paper, they use different, I mean, you have the perfect segmentation object, but you may have a contour area around the object. And you can see that in this paper, they show that it's better to leave this region around the object to get better, in this case, these parameters, sensorial accuracy or area under curve, okay? So this was another application. So just this is the end of my topic. If you want to know more, you can contact me, Xavi, or Veronica. And you may also check these links of datasets, challenges. This is maybe this MCI conference, very well known for the famous one to apply your papers if you want to work in that field, and to look for papers here to work on that. Okay. So that's it. I know it's very compressed, but it was just to give you an overview and the applications that you may find. So any question? No? Okay, so I'll leave the word to Kevin. I don't know if I should stop now. You have done that before.
I think you stopped, yeah, no, we started.